Welcome. In this session in linear data analysis, we'll explore two ways that we can formulate the residual error for an artificial neuron that has a logistic activation function. Let's begin by recalling what we mean by residual error. What we mean is that observation number I has a label that's represented as y sub I, and in artificial neurons this value is either 0 or 1. The logistic activation is a function that depends on the augmented weight vector, and it also depends on the data vector. So what we'll usually do is we think of W as varying because that's what we have to learn, and X is fixed because that's what the user or another system is providing to us as data. The residual error is the difference between the label and the output. For the perceptron model, this was 0 or 1, this was 0 or 1, so these values were either -1, 0, or 1, and now the residual error can be continuously in the range between 0 and 1, between -1 and 1. So to handle that -1 and 1, what we usually do is one of two things. Rumelhart et al. Suggested that the error be represented as the square of the residual. So this would be a least squares formulation. This is easy to differentiate. In the statistical world, they prefer to use a measure that's related to the logarithm. And what they would say is that if the label is 0, then use 1 minus the response and take the logarithm of that. Now the logarithm of that is going to be going off to minus infinity, and to make it go positive, they'll negate that. So this is sometimes referred to as the minus log or just the log formulation. Likewise, if the label is 1, then what they suggest is you just take the negative logarithm of the score. There are long statistical derivations of these equations that we won't work with. What we'll do is we'll mainly work with the Rumelhart method and observe that this other method is very common in artificial neural networks and in statistical work on logistic regression. So let's instead plot these errors so that we can get a sense of what's going on. Here we have the sigmoid activation function. So the horizontal axis is the score, is the linear sum that's coming out, and then we take the logistic function and it's asymptotically going to 0 as that weighted sum goes to minus infinity, and it asymptotically goes to 1 as the weighted sum goes to plus infinity. So this, as we understand, represents the probability that that data vector is on the positive side of the hyperplane that's represented by the augmented vector W. Now, if we take the squared error, this is what we get, is that if the label for the data is 0 and our logistic function says that it's a nearly 0 value, then that means that the residual error is very small. And if the label is 0 and the logistic function says that it's very, very probable that it's on the positive side of the hyperplane, then our error would asymptotically go to 1. Likewise, if the label is 1 and our logistic function says that it's very unlikely that that data is on the positive side of the hyperplane, then we get a maximum error, which is 1. And if the label is 1 and our logistic function says that it's very probable that that data vector is on the positive side, then we want a nearly 0 error. So if we take these residual errors and we add them up, this is the net squared error effect that we're getting. And we can see that it's a smooth function and that there's a nice local minimum to it. And that local minimum, when we bridge over to other areas of data analysis, the existence of this local minimum is an important one for performing certain iterative solutions to this problem. Now, let's explore what happens with the logistic function and the log error. Now I've changed the scale. Note that previously the scale was 0 to 1. Now the scale is going from 0 to 6. And the reason is this, is that when we have our logistic function, suppose that we have a label of 0, and the logistic function says it's very unlikely that this data vector is on the positive side of the hyperplane, then the error will be asymptotically 0. As the probability of our data vector, which is now this is a false positive, so if it's a false positive data vector, as the probability that it's a false positive increases, what's happening with this negative log error is it's going to infinity. So it's strongly pushing the, when we work this through, it will really strongly penalize misclassifications. Likewise, if the label of our data is 1 and the logistic function says it's very probable that that data is on the positive side of the hyperplane, then the residual error is nearly 0. If, on the other hand, this is a false negative, which means that its true label is 1, and we're saying that the probability of it being positive is very, very small, then in this case, the negative log error will carry a potentially infinite penalty for that misclassification. And when we put these together, what we see is this function. And here it's also smooth, differentiable, and it has a definite local minimum. And now, unlike the squared error term, this log term will infinitely penalize misclassifications, whether they're false positive misclassifications or false negative classifications. So let's summarize briefly what we've gathered in this session. What we do is we add up the error for all of the observations. So we're adding all of these curves up, and we're getting in a high dimensional spaces. The net error is nonlinear as a function of the weights, and the weight vector is what we're trying to find, right? We're trying to find a hyperplane that separates the data. And what we're trying to do is minimize the error, minimize the false positives and false negatives of this hyperplane classification. So the numerical methods are squared error is most often done using a steepest descent. We cover this in nonlinear data analysis. And then logistic regression often uses a maximum likelihood method, and in MATLAB, the generalized linear model fit function will perform this logistic regression for us. So an unusual difficult case, incidentally, for this MATLAB is exactly one of the cases that we keep coming up with, is that the maximum likelihood for separable data will drive the weight vectors to infinity, and when I run MATLAB on data, this is what I often get, is I often get a warning that my data are linearly separable. So this MATLAB is not the only numerical solver that might give you a warning.